just cancel them, get rid of them, or even reduce them if you can't cancel them out. The electrons will always cancel out because that was the whole purpose of that step before, was to get that number of electrons equal to that number of electrons. So your overall equation should not have any electrons in it because they cancel out. Every time the electrons are going to cancel out. And so now, nothing else cancels out that I can see. Now we can go ahead and bring down everything else to get a balanced net ionic equation. And then over here we have 5 Br2s, 2 Mn plus 2s, 8 waters, and we should be feeling pretty good. Now, I strongly recommend when you get to this point and you think you're done, because we should be. There were no spectator ions that we were given, so I don't know what we put in here except just leave it as the net ionic equation. But before you move on with your life, stop and make sure that this thing is balanced still, because there's so many steps involved here. Just one little error, you forgot to distribute the 2 to one of your terms or whatever, and it's throwing you off. So let's just make sure that we're balanced. We have 10 Brs on the left. There's 5 times 2, 10 Brs on the right. That's fine. 16 hydrogens, 8 times 2, 16 hydrogens. 2 manganeses, 2 manganeses. That sounds funny. 8 oxygens, 8 oxygens. So the atoms are balanced, and now we just want to make sure that the charges are balanced too. Okay, looking at the charges. Negative 10, because you've got 10 negative 1 ions there. Positive 16. Okay, you doing the math? Negative 10 and positive 16. That adds up to positive 6, yes? And then a negative 2. What's our total charge on the left? Positive 4. Right. What's our total charge on the right? Positive 4. Because that's neutral and that's neutral. Yeah? So now is the point at which we give high fives and we're done. That's a lot. Now, did I kid about taking 15, 20 minutes to do that one example? There's a lot. But I just really crawled through each step. Anybody have any questions and need a replay on something before we try another example where we maybe could go a little faster? But feel free. If there was something you missed, you thought like, man, how come he did that? Now we went on to the next thing, and I don't know why he did that. Anything at all? Let's try another example then. Another reaction that occurs in acid. By the way, tomorrow I'll show you how balancing in a base is different. Just one other step that you have to do with the base. It's not bad. Acid is a little bit easier, though. We'll kind of fix our minds on acids. But it is possible that bases will be involved too. Now this one is not a net ionic equation, but balancing this would be a nightmare. Look at all the oxygens. Everything has oxygen in it. And if we were to try to balance this thing by inspection, we'd get frustrated real fast. Just take a look, very quickly. 2 AS's there. I'll put a 2 there to balance the AS's. 3 O's and 3 O's. Let's see. Let's not do the O's next. How about we go on to something else? Hydrogens. I got 6 hydrogens, so I'll put a 6 there. That makes 6 N's, so I'll put a 6 there. Hopefully the oxygens balance out. Let's see, I have 18 plus 3 is 21 oxygens. And then over here I have 8 plus 6 is 14 oxygens. Shoot. Everything's balanced except the oxygen. What the heck do I do now? See what I mean? You can't do it without using the half reaction method. So that's where we get this method. And the reason that it's useful is because I can't balance it by inspection. We then need to figure out who's oxidized and who's reduced. So we'll take our handy rules for assigning oxidation numbers, and we'll go at it. What's the oxidation number of AS and O in this compound? Well, we know the oxygen is going to be -2. What about the AS? +3. Yeah. Okay, that's a positive sign. HNO3. Well, we know the H is going to be +1, and the O is going to be a -2. Those are our rules for assigning oxidation numbers. What about the N? 5, right. The whole thing has to add up to 0, so a -6 here and a +1 means that it's got to be a +5 to have the whole thing balance out. In the H3ASO4, once again, H is +1, O is -2, AS? Another 5. Yeah, it's another 5. That's a -8. There's the +3. So that AS in the middle has got to be a +5, so the whole thing is neutral. Yep. And then in the NO, +2, -2. Do you see who oxidizes and who reduces? Yeah? Once you have, what's that? Okay. Once you have the oxidation numbers written, just look for who goes up and who goes down. So we're going to give ourselves an ox and a red for our 2 half reactions. The thing that gets oxidized is the one that goes up. Who goes up? The AS goes up, doesn't it? It goes from 3 up to 5. So the oxidation is going to look like this. Include the entire term that it's in. AS2O3 yields H3ASO4. All right, now this is a matter of preference for me. The nitrogen goes down. The nitrogen is going to be reduced from +5 down to +2. Now, when you see this term right here, what do you know about HNO3? It's what? It's an acid. Anything more? It's a strong acid. Right, HNO3 is one of our 6 strong acids. We know that it's a strong acid because we memorized the 6. What do we know about strong acids? When it's aqueous, it does not exist as HNO3. It exists as H plus and NO3 minus. When I write the half reaction, the N is not at all attached to the H. I'm leaving the H out of the half reaction. I'll worry about it later. For the reduction, I'll just say NO3 changes to NO. Now, if you include the H, you're not dead. It will work. But I try to have as little clutter in my half reactions as possible. And so that means that if I have a strong acid that's broken apart, I'm leaving it broken apart and only including the part that changes. Now, just while I'm talking about that, check this out. That's an acid that's aqueous. Shouldn't that H and ASO4 be broken apart? No. In fact, what do you know? What's fresh in your mind is your lab. Have you seen lately a triprotic weak acid? That's in your lab. Yeah. And when you were doing the particle drawing of that one, should the H be broken off of the ASO or whatever the A was? Nope. By the way, H3ASO4 is not in anybody's sample. But yeah, don't break the hydrogens off of the anion when it's a weak acid in your net ionic equation. They stay together. Some of the molecules release their hydrogen. Most, the hydrogen is still on there. So that's the way we draw it. Are you listening and you following that? Is that the way you drew your particle drawing? I hope so. It should be. Okay, so I have just thrown away some of my time. Let's move on this thing. The steps for the balancing the redox. We've got everything written out as half reactions. Let's go for it. Balance all the non-H's and O's first. I have 2 AS's over there, only 1 AS there, so I'm going to put a 2 there. The rest of that oxidation half is H's and O's, so I'm leaving. In the reduction half, I got 1 N and 1 N. I'm done. So I'm done with that step. I've balanced all my non-H and O atoms. Now let's go to the oxygen with a different color. I have 3 oxygens on the left. I have 8 oxygens on the right. Oh boy. So what do I do to balance the oxygens? If I have 8 on the right, I needed 8 on the left. So if I started with 3, I need another 5 oxygens. What does it look like though? Water. Yeah, it's water molecules. Or just put 5 overs. Again, and the reason for this is because oxygen is so reactive, it doesn't stay by itself. It gobbles up water molecules right away, and there's your oxygen that's in the form of water. So let's do the same thing for the reduction half. I got 3 O's there and only 1 O there. So I need another 2 oxygens over here. That means 2 water molecules. I set that marker down. Let's go on and do the next step. The next step is balancing the hydrogens. Now we've got the oxygens done. Now the hydrogens, watch carefully. You have 10 hydrogens here, but you also have some hydrogens there. There's 6. So I need another 4 hydrogens over here. The hydrogen's going to be in the form of H+, which goes right into this acid environment, which is fine. In the reduction half reaction, I don't have any hydrogens over here, but I have 4 there. So I need another 4 hydrogens over here. We good? Okay, so now, once you've gotten the hydrogens done, if you've done everything in order, our atoms should be balanced, but now the electrons need to be added in here, and we need to account for the charges. So let's see, I've just done blue. My next step is acknowledging that the oxidation gives off electrons, the reduction takes in electrons. How many? So I look to see that the electrons are in the products of this. To balance the charges, I'm going to look at the opposite side of the arrow, the overall charge. That's neutral and that's neutral, so the left side is neutral, yeah? The right side, though, is not neutral. That's neutral and that's positive 4. How many electrons? 4. Now the reduction half reaction, same thing. The electrons are on the left, so look to the right and check out the charge there. Neutral, neutral, so the right side is neutral. The left side, without that term right there, what's my charge? Positive 3. So if that side's neutral, I got a positive 3 over here, how many electrons do I need to add to take that positive 3 down to 0? 3. Once in a while you get lucky, and that number of electrons and that number of electrons are equal. So you just add them together and you're done. But unfortunately, we're not lucky. I got 4 given off and 3 taken in. What do I do? We need 12 on both sides, don't we? So that means that the oxidation half has to get multiplied by 3, and the reduction half has to get multiplied by 4. Okay, if that's what you want. Let's rewrite these things, distributing the 3 and the 4 in very little time. So with the 3, I've got 15 waters and 3 As2O3s, not plus, yields 6 H3ASO4s and 12 hydrogens and 12 electrons. The reduction half reaction, distributing that 4 now, 12 electrons, 16 hydrogens, 4 NO3 negatives, 4 NOs, and 8 waters. Okay, so when we're ready to add these 2 half reactions back together, again, I look to try to clean things up before I have them all added and jumbled together. So the electrons I know are going to cancel out. That was the purpose of the step before. They had to cancel out. You can't have 3 electrons. What else can we do with this to clean it up? You see any terms on both sides? There's waters on both sides. Now they don't totally cancel out because I got 15 on the left and only 8 on the right. So I can, though, reduce both sides by 8. Just subtract 8 waters.